Hi Axel, hi, check.
Here, maybe I start again, since we have guests in Russia. So I start again. So dear Professor Graetzel, dear Mrs. Naumova, dear Mrs. Chinina, dear Dr. Karlsruhe, dear colleagues, ladies and gentlemen, it's my particular pleasure to welcome you here at the lecture of the 2017 Global Energy Prize laureate, Professor Michael Graetzel, on the energy of knowledge. So we are all very much looking forward to this lecture. Until then, you have to listen to two more presentations, because we are very proud as the Karlsruhe Institute of Technology to host this first lecture of a lecture series by Professor Graetzel here at Karlsruhe. And so we'd like to take the opportunity, and we are very thankful that we have that generous opportunity to present briefly our research on energy-related topics at KIT. Then, of course, the lecture will be given by Professor Graetzel, and in between, Natalia Naumova will explain us a little bit about the background of that and the entire presentation of the Global Energy Prize. So that's the outline for this afternoon's presentations. So let me start with a few introductory remarks with respect to the Karlsruhe Institute of Technology. As you see on the first slide, so we originated from, on the one hand, from the University of Karlsruhe, which was actually founded in 1825 as a polytechnical college, and then became later in the 19th century a technical university. About 60 years ago, the nuclear reactor and construction company was founded just outside of Karlsruhe, where the first nuclear power plant in Germany was built, and then much later, just a little less than 10 years ago, these two organizations were merged to the Karlsruhe Institute of Technology, which is now the only, and it's a really unique setting in the German landscape, is a university and a national lab at the same time. And that's why we call ourselves the research university in the Helmholtz Association, which indicates that unique setting. All right, when we look into now our mission, then basically, of course, we're doing research in a number of fields, and I'll get back to that in a second. Of course, we do higher education, and then as a third mission, we have innovation. So it's really one of our particular aims to really bring things that we develop at KIT to the market, and you will hear a little bit more about that later, I guess. And one of our specialties in order to foster interdisciplinary research at KIT is that we have what is called KIT centers, and one of these centers is the KIT Energy Center, and there are 6 more, and I explain that on the next slide, or one of the next slides. But before I get to that, I'd like to give you just a little bit more of history. So here you see a number of alumni from Karlsruhe. Some of them go really back into the 19th century. So for instance, Heinrich Hertz discovered the electromagnetic waves here in a lecture hall, which is just 100 meters from here. And there are a few other very well-known people. Actually, one person is missing here that I'd like to mention. This is Otto Lehmann, since he discovered liquid crystals. And when he did that in the late 19th century, this was really very fundamental research and not related to any application. Actually, he himself said at some point, or wrote at some point, maybe they're not good for anything, but they're it's really fun to study them. And then about 100 years or 80 years later, this became a $1 billion market in terms of all the LCD displays that we're using these days. So I think it's a very nice little history on showing how fundamental research on materials can change at some point really technologies and influence the life of many people in a way when we think about all our smartphones that are relying on that kind of technology. And that's pretty much along, I think, the lines of what Michael Graetzel did his in life, to studying fundamentals of materials, trying to understand them, and then at some point bring them into an application that mankind can take profit on. And I think that's part of why you received that wonderful prize on global energy. A few facts and figures, so I run very quickly through that. So I think, as I pointed out, we are, as I said, university and a national lab, so we have quite a number of employees. Among them are more than 3,000 doctoral researchers, actually 3,200 as of the beginning of this year. We have a faculty of a little less than 400 professors, almost 26,000 bachelor and master students. So this is, in a sense, a mid-sized university compared to some others in Germany. But again, within the combination with the national lab, we're fairly large. And the billion is getting closer to €1 billion per year. And about 40% of that are third-party funds that we receive from many different organizations. So I already mentioned the so-called KIT centers, which are interdisciplinary in nature. With them, we address sort of the big challenges in science. You can read through them. So as I said, I already highlighted the one on energy, which is of course relevant to this event in the afternoon. But there are others, for instance, on materials, or there is one on information, which is of course these days a very hot topic in many respects if you think about artificial intelligence, quantum computing and the like. So I think we are active here in a number of things. And as I said, they help us to bundle our research, our platforms to plan and discuss strategic areas of research, also to go reach out to the public. For instance, the KIT Energy Center had recently an event in the City Hall where scientists presented what we are doing in the area of energy, and to have the opportunity to discuss with people basically what we are doing, why we are doing that, and what how in which sense that might be relevant to the public. I'm not discussing that slide. I'd like to point out that the Energy Center is the largest of the KIT centers. We have roughly 1,500 scientists and technical staff being being active in this area. You see there are a number of different topical areas in energy, and Alexander Karlsruhe will explain that in more detail and highlight some of these activities. So I'd just like to point out that energy is really a very important research area at KIT. This is also related to some of our large-scale infrastructures that we run, and again I just highlight ones that are relevant to energy. So there's, for instance, what we call the Energy Lab 2.0. This is, on the one hand, some units that produce energy, so to speak. So you see, for instance, a photovoltaic park there, but there's also a big lithium-ion battery rack, so to speak, and gas turbine and other devices. And what we do there is simulate how an energy system could work when there are volatile components like sun involved, and how to manage that kind of, basically volatile energy system, both from the hardware side as well as on the software side. Other large infrastructure is depicted here. This is what we call our BioLic plant. This is to produce liquid or liquids from biomass, like synthetic fuels and the like. And this one here is not directly related to energy. This is sort of the largest vacuum on Earth, where we try to measure the mass of a neutrino, but this is only possible because we run also the tritium lab in Karlsruhe, which is highly relevant for fusion research as another option in energy, which maybe is only relevant in the second half of this century, but still is an option how to produce energy at low cost, in a sense, in particular low CO2 cost. I'd like to point out, and with that I particularly address maybe our colleagues and students in Russia that, as I understand, are listening to us in 6 to 8 different universities in Russia at that time. So also a very warm welcome to you. I'd like to point out that Karlsruhe KIT is a very international place. You see here some characteristic numbers without, again, going into much detail. Roughly 20 to 25 of our students and PhD students are having an international background and coming from abroad to us. And again, I'm not discussing these numbers in more detail at that point. Actually, instead, I open the stage for Alexander Karlsruhe to talk a little bit more in detail about our activities in the area of research. Thank you very much again for having us, so to speak, hosting this event. We're very proud and very privileged to have that here, and I'm personally very much looking forward to the lecture by Michael Graetzel. But again, first I invite Alexander Karlsruhe to the stage. Thank you.
Yeah, thank you very much for the kind introduction. Dear Professor Graetzel, dear guests, dear colleagues, dear listeners at the video screens in Russia, I would like to give you a little bit of an overview of the energy activities at KIT. KIT set out to become one of the leading research centers for energy, and this is reflected in the Energy Center, one of the 7 interdisciplinary KIT centers that Oliver Kraft already mentioned before. And if such an institution like KIT engages into energy research, then our mission cannot be any less than shaping the energy landscape of the future. We want to make a really holistic approach. We want to address all the various challenges that needs to be addressed to solve the urgent energy questions of the future. This means we need to gain our energy somewhere. This will be renewable energy in the future. If we produce the renewable energy, then we also need to store it, we need to distribute it. So this is what you see on the right side, the storage networks, the systems. And of course, it's not only about producing energy, but it's also about using energy more efficiently. So those are all the tasks that KIT is dedicated to. And KIT put a lot of money into this research. So again, you see a lot of large-scale research infrastructure, whereas in the previous presentation, this was general KIT research infrastructure. Those items shown here, they are all related to energy. And I can probably shorten this a bit because the most important things have already been highlighted by Professor Kraft. So we have this large biomass plant here, the BioLic, the energy lab was already mentioned, and also what I like a lot is the Selightment. This is a concept to produce cement with very little energy. So if you look at the energy balance of cement production, a lot of energy goes into the production, and KIT found a concept to reduce this energetic effort. To master all those challenges, KIT has, as I already mentioned, invoked the KIT Energy Center. And the KIT Energy Center is subdivided into 7 topics that cover all those aspects that you have seen on the previous slides. The KIT Energy Center is a virtual institute, if you like. It's a large entity, but it's virtual. So we have different institutes collaborating under the umbrella of the KIT Energy Center. And for example, I often get applications from students. We would like to work at the KIT Energy Center, and I always have to write back, well, that's not so easy because we don't have a building or something like that. You please have to study which institutes belong to the Energy Center and to look which suits you most. 60 institutes is quite a big number, all working on energy, and there you can see that KIT really is serious about energy research. I would like to quickly talk you through the most important aspects of the KIT energy research, and I will do this quite quickly. As you have seen on one of the introductory slides of Professor Kraft, the northern part of KIT, the former research lab, the former National Research Lab, has its origin in nuclear research. As you all know, it's very unlikely that further nuclear plants will be built in Germany, but we still have to deal with the nuclear waste. We have to deal with the power plants that are already there to make them safe. And so nuclear safety is a big topic for KIT, and that's still going on at Campus North with all the knowledge that we have from the nuclear research before. If we look more into the future, if we think of some energy systems that comprise all those aspects, then of course we need first of all an energy systems analysis, because we need to put all those pieces together and to make it a working system. And that's why we have this topic on energy systems analysis, where we really look into the networks and the interplays between the various components of an energy supply in the future. Part of this energy supply in the future will also be a very good storage. So we need to care about energy storage, which is batteries, which can be hydrogen storage, for example. All this is done at KIT. If you think big, you need storage. For example, if you want to use renewable energies, you know, the wind does not blow all the time, the sun is not out all the time, so you need to store the energy for the time when you need it. But also if you think small, if you think about cars, if you think about electromobility, you need all those batteries and similar concepts. And then we need to distribute the energy, so that's why we look into smart grids that are adapted to the requirements of this distributed energy generation. And we also look into new kinds of grids. For example, can we use superconduction to make it more efficient? Those are all topics that are under the umbrella of energy storage and distribution. Then we need energy conversion. Of course, we need to convert one form of energy into another. We look into materials, into concepts, models and device simulations. All this is part of energy conversion. Energy efficiency is very important. We look into industrial processes, how to make them more efficient, how to make buildings more efficient. You all know that we are in desperate need for zero energy or zero emission buildings that do not consume more energy or that can generate all the energy that they consume. This is the topic of efficient energy use. And then we also need to consider where do we get our energy from in the future. And one concept, this will not be tomorrow, but maybe in 10, 20, 30 years' time, maybe fusion technology, and gaining energy from fusion. And this is also a topic where a lot of manpower goes in at Campus North at KIT. And finally, of course, we have the renewable energies, which will be the source of energy of the future. And now we're again moving a little bit closer to the topic of our symposium here today, because one of those topics, of course, is also photovoltaics here at KIT, the topic that Michael Graetzel is the expert in. And I would like to briefly give an outline of what we do in photovoltaics at KIT, because it fits nicely to the symposium today. But I have to say, I can only give you a glimpse of what's going on. Last time I counted, we were almost 40 PIs working on photovoltaics here. So this is really just an overview. We look into many different material systems, mainly thin film solar cells. There are the castorites, the perovskites, carbon nanotubes are used in solar cells, organic solar cells, CIGS. And we also have groups that simulate materials towards finding new energy harvesting materials for the future, which is here depicted with this in silico material design. We also build devices from small scale to let's say not large scale, but mid scale, from all those various technologies. So, for example, here you see one of the records that KIT contributed to, a stacked CIGS perovskite tandem solar cell. On the right side, next to it, you see an organic solar cell. We presented those organic solar cells last year at the Hannover Fair. We had some smart solar glasses that we exhibited at the Hannover Fair, where the solar cells were integrated into the glasses. You actually looked through your solar cells when you had the glasses on your nose. We also follow a lot of photonic concepts to improve the light harvesting of the solar cells, and as such a large research center that KIT is, we of course also have all the world-class characterization systems that are needed to characterize materials, to characterize devices, and also to simulate devices. And the interplay between simulation and characterization, material design allows us to really develop a deep understanding of what's going on in those solar devices. So with this, I'm through, and I would like to move on to the next presentation. So when I started to study physics 20 years ago, I can remember our professor tortured us a lot on optoelectronics, and one thing he tortured us particularly on was the Graetzel cell. Back then I was not bold enough to really understand how this thing worked, but there were fortunately others out there who did. And I thought back then, when looking at all the photovoltaics technologies, when you get to that point that a solar technology has your name, then you really made it. Because the Graetzel cell is probably the only solar cell I know of that is named after its inventor. And so I think Professor Graetzel is really worthy laureate of the Global Energy Prize. And this is, yeah, well, for a prize, we always need someone who actually pays the party, if you like. And so it's my pleasure to welcome Mrs. Namova from the Global Energy Prize, and the stage is yours.
Okay, thank you so much for these kind words and introduction. First of all, let me say on behalf of the Global Energy Prize that it's a great opportunity for us, and we are really happy to be here and to give a lecture of our laureate. That's our first initiative within the KIT, but take into account to your background, to the great work you do in terms of research and energy, that's really precious to us to be here today. So, as you already understood, Michael Graetzel, who is giving the lecture, is our laureate. He received the Global Energy Prize last year for the development of those cells, the Graetzel cells, and that's also the only solar cells I know. He will tell this perfectly all by himself. In my turn, I would like to present the Global Energy Prize a little bit more to you. So it was established in Russia in 2002 through the Global Energy Association, which I personally present, and with the support of leading energy companies, as you may see, Gazprom, Surgutneftegas, and FGC UES, which actually stands for Federal Grid Company of Unified Energy Systems. And what I may say is that these companies support the prize because they stand for the belief that advances in energy, in science, in technology is really crucial, and it serves the long-term interest of human development. So that's why we are happy to have them on board. Having said that, I would mention that the key areas of the focus of the Global Energy Prize are as follows: recognition of achievements in the field of energy that benefit whole humankind, promotion of international scientific and energy cooperation, popularization and development of industry research. Let me just note that for 15 years of its existence, the prize has united among shared goals of solving energy challenges, great network of global experts. Thus, since 2003, the Global Energy Prize has been awarded to 35 laureates from 11 countries. We have the Global Energy Prize International Award Committee. They have the selection of laureates, the final choice of the selection of laureates, and those people represent 11 countries. We also have a great network of international experts that evaluate each candidate for the nominee, what else? We annually organize Global Energy Dialogue, that is the Global Energy Prize Summit. We think that's a really crucial initiative to get together different experts from different backgrounds, different countries, and they all work out some solutions to energy challenges that are really crucial. So this is the beneficial situation for all of us, if there are some great minds that could solve these issues. And this year, the summit will be held in Italy, Turin, in April 18th, and the theme of the event is modelization and simulation of energy mix in the future digital world. So if you don't want to miss this hot debate, please know that this event will be transmitted live at euronews.com, and as well, you could always go to our website, which is www.globalenergyprize.org, and see all the latest details there. So on the eve of the event, there will be a special link to the transmission page, which will be on the Euronews website. So if you don't want to miss it, just please use our website, you will see all the information there. Basically, talking about other initiatives held under the auspices of the Global Energy Prize, I would like to highlight we also have different programs that are tailored to younger generation and aimed at inspiring them into innovation. Namely, this very lecture is held within the program The Energy of Knowledge. We believe that it's crucial to spread the knowledge of our laureates. That's why we hold lectures in different countries. And as I mentioned already, this time it's our first time at KIT, but we hope that this cooperation would flourish. We also, among other programs, we have the Energy of Start, which is the program for high school students who develop different technologies also related into the energy field. And within this program, we unleash the most promising teenagers. We believe it's also crucial that they choose energy and science as their future career choice. We also have the Energy of Youth, which is the all-Russian contest for research projects between scientists under the age of 35. They get a personal grant. Basically, these are the money that they could use into their research, and each winner gets 1 million. That is approximately 14,000 euros. So that's how we try to strengthen their research. We also have the Energy of Breakthrough. That is the program for scientists under the age of 45, and they get personal prize, monetary reward, also 1 million rubles. So as you may see, basically all our programs are used by us to popularize the industry research and strengthen cooperation. What else should be noted is that the Global Energy Prize is really international and independent in terms of how we select our laureates. As you may see, no self-nomination. Self-nomination is not applicable. And only experts of nomination pool could use the right and eligible to nominate a candidate for the prize. In total, for all the years of the Global Energy Prize existence, citizens of 19 countries have already participated in this process. And if you want to know more on how to become a nominator, you could always go by this website and you will see this red button, Become a Nominator. Just press and then you will see the information that you could use for that. So just once again, here's the link, nomination.g-prize.org and log in. Or simplest way, just go to the Global Energy Prize.org and you will also see the special tab nomination. This is also a really precious moment for us because we also have a book, the Global Energy Prize, Tribute to Those Who Changed the World. Because all our laureates have inspirational stories and there is a special chapter on Mr. Graetzel as well. I guess after the lecture you could upload this book. And the last but not the least, also last year we produced a film, the Global Energy 2030 film. We tried to foresee how our future will look like in 2030. And basically this film shows how the technologies change our life, and of course among those technologies are the technologies of our laureates. I don't want to take much of your attention, just let's have a short preview.
The future has arrived. The world has changed.
We reached a stage where we are simply overheating the world. We need all the best talents of the world.
We are in the year 2030. In the Global Energy 2030 film, you will see the real future. Our capabilities have become limitless. Robot assistants, smart home with only one click. Living with comfort is a common practice. We have learned to use things that used to kill us before. A pair of volcanoes, the sun, wind, water, and an energy-independent planet is ready.
I want to go to space, and energy is no longer a constraint.
The fluorescent Rosenfeld lamps, the Allen cycle, the Graetzel cells, the battery by Elon Musk. The inventions of 2000s opened a window to our future.
You know, energy is so fundamental to everything that happens in the world. It is the lifeblood of economy and of society.
And I would say that work at the Global Energy Prize helped a lot in creating this situation.
Is there an elixir of eternal life? Is it worth colonizing the moon? And how does garbage save the environment? Open the world together with the Global Energy Prize.
So basically this is it. I'm pretty much done. Thank you for your attention. And Mr. Graetzel, the floor is yours. Just a sec.
Thank you.
So while everyone gets set up here in front, I should use the opportunity to introduce our guest. Well, does he need any introduction? I think pretty much everyone has heard about Professor Graetzel, and I will just quickly pick some numbers from his quite impressive CV. So Michael Graetzel has graduated in 1968 from the Free University of Berlin. In 1976 he earned his Doctor of Science in Physical Chemistry, and since 1977 until today he is a professor at at the Swiss Federal Institute of Technology in Lausanne. I found some more numbers that were quite impressive. One of them is that he authored or co-authored more than 1,300 publications. That's a lot. So for our PhD students, remember you need 3. He holds 50 patents, which is also quite impressive. And so far, he is the only one with a solar cell named after him. So do the best to match. So with this, I think enough of words. The floor is yours, and we're looking very much forward to your presentation.
Thank you. It's a pleasure and honor to be here. And so, well, first of all, I'd like to thank Vice President Oliver Kraft for chairing this memorable event. And our guests from Russia, Natalia and Anna, it's a pleasure to see you again after almost 1 year of a break. And all the students in Russia that follow this lecture. So it's a great pleasure to speak in front of you. And all the students here, all the participants, thank you for coming. And so, last but not least, Esther Legend has been a very good host in organizing my trip here. So thank you so much, Esther. So the lecture today is should give you a flavor of our work. It's not a deep scientific analysis. Okay, so it's just to show you where we started and how the field of molecular photovoltaics and also perovskites that actually evolved from that field, how this development took place and what was the rationale behind it. But to start with this critical moment in St. Petersburg last year on June 2nd, we were all very nervous, and it was a beautiful ceremony, and so I was asked to give a short talk, and also the Russian energy minister Alexander Novotny was there, and it was a big honor to get the prize from him directly. So so the talk is on mesoscopic photosystems, and I won't go through my CV. You can follow that on the internet. And so the world's energy scenario, that's just a short introduction, and I will go through these points very briefly, and we have about 30 minutes, and then feel free afterwards to ask me questions. So, I mean, the planetary emergency is pretty much clear. We have this very unpleasant situation with pollution is married to global warming, the gasoline running out, and nuclear risk. So especially, I mean, the pollution issue will limit future use, exploitation of fossil reserves. You see the warming effect, climate change, and some of the accidents that happen actually too frequently. And so the issue then is that today we are consuming 18 terawatts. That's a power consumption. So if you divide this by the number of inhabitants on Earth, you get to 3 kilowatts. So that's everybody is continuously consuming 3 kilowatts. But we need only 100 watts to stay alive. So already the average is 30 times the need for life. Okay, so there's a big exaggeration. So the first thing is one has to save energy. But then there is still the saving. I mean, despite of that, we will have a growth in energy consumption. And so how to cover these remaining 15 terawatts? That's an analysis done by NREL. And so, I mean, there are not many options. The quest for clean and renewable energy. And so there are many ways, wind, biomass. Actually, hydroelectric, wind, biomass, solar. That's all solar in a way. So let's not forget. But today we will be talking about quantum conversion. And so the financial means will be there. So just this is some analysis that was published a couple of years ago. So $1 trillion will have to be invested in photovoltaics in the next few years. So photovoltaics is growing, and there's some issues with silicon, high capex, and marginal value is low. In other words, the profits and the grid also. It's even a 10% feed-in. The grid starts to. So we have to go to decentralized. We need actually an even cheaper. Silicon has become quite cheap. Even cheaper technologies, and so that will drive the growth further. But today we have about 350 gigawatt. That's peak power installed, peak power. And so that doesn't mean 350 real power, because the sun is not shining all the time. Okay, so we have to divide this by at least in Germany a factor of 7, so get down to 50 gigawatt, but we'll need about 50 terawatts, so there's a scale of a factor of 1,000 still to come. And so that means all of you are welcome to make new inventions and drive this. We need the young people to come in there. Very warmly welcome, and so there's room. This is not a game that has been played. It's a game that is starting. And so, well, from our point of view, photosynthesis showed us the way, because after all, in photosynthesis, we store, the power stored is 90 terawatts. That's sunlight to stored chemical energy. And so that's about, remember I said we had 18 today, so that's about 5 times what is consumed today on Earth. The photosynth managed to store that from sun. With a small efficiency, but it's stored energy, and we are living on this. Fossil resources come all from photosynthesis. And so, but the photosynthetic conversions are used a molecular system like this dye-sensitized solar cell, where we have chlorophyll in the green leaf. Here in the dye-sensitized is the sensitizer. Excitation, carrier generation from the molecule, from the sensitizer, and then carrier collection in the green leaf. Fuels are produced, so oxygen and CO2 is reduced. But here with that cell, we take the electricity out. So the molecular photovoltaics, they mimic the photosynthetic elementary process, a light reaction photosynthesis, there's no doubt. And but when we started on this project, we were strongly discouraged by our mentors that told us, don't touch it. 2 reasons: the efficiency of these cells was extremely low, probably less than 0.01% conversion efficiency, and the stability was also very poor. So my teachers told me, doing the wrong thing if you go in this domain. But that was the wrong advice. So again, the young people, one should never be dogmatic. Okay, you should even sometimes bet on something that is perhaps unlikely to succeed, but with your brilliant ideas, you overcome the problems. And so, yes, our ideas were to actually, it wasn't invented one day. We had long gestation where we did fundamental research on nanocrystalline TiO2 particles in solution using laser spectroscopy. And we found that we could sensitize those particles very efficiently. And especially, we measured that the injection and recombination were a completely different timescale. Injection happened in a few picoseconds, recombination milliseconds. So there was a chance to collect those carriers that were injected in a photovoltaic device. So that led us to this three-dimensional electrode at a time when everybody said that you need a planar p-n junction to convert sunlight to electricity. Here we have nothing planar and we don't have a p-n junction. But we have a system that is based on molecular light absorption and charge, photo-induced charge separation based on kinetics and not a local potential field. So here you see the effect, planar, very little, 0.1% of the incoming photons, maximum convert to electron. So that's very, very small efficiency. Now, if you just go to these particles, so the white dots are the nanocrystalline TiO2 particles. We were the first to make those particles. And we make them in the film, and the dye was absorbed from solution, over 90%. So you go from a system that is extremely expensive and produces photons in a nanoamp range to a very cheap film system that produces milliamps. So we had 10,000 times increase in photocount by changing just over the three-dimensional electrode system. And so the virtue of the nanostructure, well, the internal surface area is very high, so you concentrate the dye in this nanoparticle network. It's only coating a monolayer on these particles, but since you have many, many particles, like in the green leaf, you have stacked thylakoid membranes, you will absorb the light. And then you extract the carriers selectively, only negative charges are extracted, by using those large wide bandgap materials like TiO2 that have a band, the conduction band, at the right level to take up the electron and transfer it to the current collector. And then another feature is, these are insulating films, so how come we can use them to collect carriers? Well, the inject electron turns the nanoparticle from an insulator into a conductor. And also, you can inject many electrons without having the Coulomb blockade effect, because the ions on the surface screen that electronic charge. So finally, this configuration came out, and was paper in Nature. You see the nanoparticles and the TiO2 nanoparticles, and dye on the surface, and injection, carrier collection. And so you need to bring the electrons back once they left the cell. You have to bring them back to the dye. So we use iodide triiodide redox shuttle. This has meanwhile evolved, and there are more powerful redox couplers. So patent application was filed, and for a while it says one patent in '88, and then nothing. And today we have over 3,000 patents from the DSC field. And this was the paper that we published in Nature a long time ago, but it shows the cell with looks like a tainted glass, and you see the fan turning on ambient light. That's one of the features of this device, is that it captures light from both sides. Okay, so it's bifacial, and it's very efficient, like the leaf in harvesting ambient radiation. And so today, we can show that for ambient light conversion, this is the best photovoltaic around, even better than gallium arsenide. I'll show you some example later on. And so this paper has actually become one of the most highly cited research of all times. So that's not I am telling you that. It's an analysis by Nature several years ago. And you can see how the citations went up. I'm not trying to brag about our citations, but it shows that the work had a general impact. And why? Well, because we went from this stereotype, archetype p-n junction concept to something disordered and three-dimensional and nanostructured. That was supposed not to work, but it worked extremely well. And so today we have new dyes. It's a green dye, the donor acceptor. It's a whole science that deals with designing and theoretical modeling of dyes. And that's one successful candidate we will actually develop together with some colleagues from Taiwan. And it became the green dye, which is now, it had 12% conversion efficiency of full sunlight to electric power, which was at that time a record for dye-sensitized solar cells. And it has that aesthetically pleasing appearance. Okay, and so industry became interested in it. And well, maybe we can do something with these green panels. And so we did some modeling also on the molecular structure to improve the dye further. And this is just a LUMO-HOMO picture of the orbital distribution. So we did our homework. We went into great depths to understand this particular sensitizer. It has a donor acceptor function. And also how it was tied up to the TiO2 surface and how charge separation happens. When you excite the dye, electron flows from top to bottom. And so then the negative charge is down here, positive charge is up there. So the recombination is slow because it has to go over a long distance. So that this charge separation is maintained over 1 second, several seconds. In a silicon cell or gallium arsenide, the charge separation electron hole pair is a few nanoseconds or microseconds. And so now we see some applications of these panels. There's a company called H-Class in Switzerland, and they're just scaling up to a production volume of 200,000 square meters per year. And so this is now becoming actually penetrating in the private market. I myself have ordered one of those green fences for my orchard, and I have also the car charging station next to it. So I'm driving a plug-in hybrid so that you can use the battery, store it. And I already have announced our electricity company in Lausanne that in the future I will put in electricity, not pull out electricity, and how much money I would get. Okay, so they told me. So this is a car charging station. It's exactly doing the thing I want to do, but it's industrially produced. The other panels too, but this is next to the production site of these green panels in Fribourg, Switzerland. This is a first electric power producing a sound barrier and or noise barrier, and it has produced the first year 1 megawatt or several megawatt hours. So it's not a negligible amount of electricity. And this has been monitored. This is strictly by our energy office in Switzerland. So they cannot claim they have made several gigawatt power electricity. This has all been monitored continuously. And and then we have also I mentioned to you the low light or diffuse light applications, ambient light. And I just want to mention to you that by designing the dye structures and also the redox shuttle, these copper complexes, we can make cells that have this solar cell that have that appearance. It looks again like a tainted glass. It has the EPFL logo. But I mean, if you look at our paper Nature Photonics last year, you see that actually with that configuration we were able to beat gallium arsenide as our competitor. It's the best photovoltaic around, the p-n junction photovoltaic. And so, so now let me move on and talk to you a little bit about the perovskite cells. And they evolved from the dye-sensitized systems. And well, I mean, a lot of it's well known, the perovskites, they have been used as an oxides, ABX3 structure. And so a lot of work has been carried out on those halide perovskite recently. And here's some of the attractive features: strong light absorption, tunnel band gap, small exciton. All this is attractive. It's not exceptional. It's not exceptional except for the low defect concentration. that happens because we have an unusual band structure. Okay, see, the material has a valence band maximum that is mainly formed by anti-bonding orbitals. So it's an amazing situation. So that you don't have a lot of defects in the band gap. You don't want to go through the physics right now. And so that has led to this amazing rise of the perovskite. If you want to read about the earlier work, just follow this review paper. And you see actually the number of papers published. It was about 3 in 2012. And last year we had over 3,000. So it went from 3 to 3,000. 1,000 times more papers published in a few years. And here's the first one, which one of the first Namgyu Park. We then, in 2012, we joined up with him and we came up with a solid-state version of this sensitized systems. At the same time, Henry Smith, one of my former postdocs, he published in Science. So these two kind of triggered the evolution we have seen, that amazing evolution that is still amplifying. It's hard to stop. I just was in China and was overwhelmed how many people worked there on perovskite solar cells. And so we have made some fundamental innovations in this field, and we also have found that actually when you do the mesoscopic structures, you can fully infiltrate the film. Before, remember, we put the dye only on the surface of the nanoparticles. Here you can fully infiltrate the film with the pigment. And that's shown here by this elemental mapping experiment. And when you do that, you save space because now your absorption length is greatly shortened and my monolayer doesn't absorb a lot of light. And so we go from a few microns to a few hundred nanometer. That's the typical film thickness now. And so also complex structures have been used, like these multi-cation. So there's need for theoretical modeling. We do a lot of NMR experiments to figure out what's really going on in these compositions. And so structural characterization is very important. Here's the efficiencies. It went up to, the last certified value was 22.7, but we have recently in our lab measured 23.25. Still have to certify, but it's promising. Okay, so the curve is continuing to climb up. So that tells you that if you take the 22.7, you're already better than the market leader, multicrystalline silicon. That's for the laboratory cell. But these values are also measured for laboratory cell silicon cells. So just to give you the flavor of our current work, we have recently found that molecular modulators are very important to affect the recombination of electrons and holes in these systems, and especially at interfaces. And so we came up with this so-called SN structure, and we used it in a double cation. That's the most stable perovskite formulation, former metallium cesium, and it has a very good light absorption in the near infrared. And so you see here that the gist of the measurement is we can show that just by adding a little bit of this compound in the precursor, we get a slowdown factor of 10 in electron hole recombination. And green curve is with the modulator, and the red curve is the blank control. And here we have written the kinetic equations for this, and we can extract from the decays the rate constants. And here's the radiation loss time constant. See, it's going very high. It's going approximate factor of 10 up. I also want to mention our friends at Moscow State University, Alexei Tarasov, who came up with we have a joint project with the Swiss-Russian Science Foundation, and our friends came up with a totally new process to make the perovskite. They can turn elemental lead in one step, just some magic, in one step, they turn elemental lead into phosphide. And how is that? Well, they treat the material here's the paper, new formation stratified via room temperature reactive fully iodized lead. So we're taking the methyl ammonium iodide and they turn it into triiodide. So we have an oxidant triiodide and the methyl ammonium iodide, which serves to form the phosphide from the lead. And so one step for exposing here you have a lead surface and you dip it into this melt and you get the phosphide. So it's amazing what you can do if you come up with new preparation concepts. So this is a group of Alexis Tarasov, and I like to mention also Andrei Petrov, who has been with us as a master student, and Andrei Shevelkorov and Eugene Budlin. These are some of the friends of colleagues that we are working with at Moscow State University. So at the end, who will win the race? Well, we have now a newcomer, still perovskite still developing. There's no, you cannot buy perovskite solar cells. You can now buy dye-sensitized solar cells, but not perovskite solar cells. And well, it's still early. You have to work more carefully on the stability of these systems and increase efficiency still there. I mean, there's lots of room for improvement. And so cost is low, efficiency is high, stability we have been able to improve. I show one example where it looks very promising. And so here's the cost performance analysis and the levelized cost of energy, that's of electricity. That's what the client is interested in. The client wants to know how much money do I have to pay for kilowatt hour if I use your photovoltaic cell. That's at the end. That's what he wants to know. Okay, and so you can see the comparison here with other systems like silicon, solar, and PSC featuring a target price of 30. That's US dollar per megawatt hour, so it's 3 cents per kilowatt hour. So that's a very low cost analysis. The cost analysis, very low target. Yeah. So unfortunately, I have to tell you that with the fuels, we are running out of time. So I have to jump through that, and it will be another talk. Okay. And let me now, at the end of my lecture, let me tell you a little bit about the applications. And well, of course, the industrial applications today come mainly from dye-sensitized solar cells. And so today we have these Internet of Things applications, and that's for flexible type devices. Some of the, when I was in Russia, I showed one of those backpacks, and somebody in the Mariinsky Theater, when I went for the evening performance of the Nutcracker Suite, he recognized me from television, and said, "You were this backpack," and I had to sign. So that was amazing that this person had recognized me. I was just being there as a spectator. And so here's some other persons that he gave one to Bill Gates. I gave one to Bill. This is a visit of the Al Gore from former vice president. These are commercial cells that are now made to hundreds of thousands of square meters. Powering like e-readers and tablets. A company is called Exeger is producing in Sweden. You have the internet connection up here, and so if you're looking for a job, there's an opportunity in Sweden. Okay, we we're very proud about our convention center in Lausanne. Please visit, which is equipped with these dye-sensitized panels. A very beautiful image from inside. And as I said, we have those H-class and other companies producing modules in Korea, in China. And this is the new science tower that was inaugurated last September in Graz, Austria, featuring 1,000 square meters of DSC panels. And that was really a nice site. They invited me for the inauguration. It's amazing how this building was finished in time and all the functions they have in this tower. So please visit when you happen to be in Austria. And so the market share is expected for perovskites 9.3. The market is big. It's something like $80 billion right now. So 9% is not a small amount. And if you look into the dye and stress also, it's very similar, about 10% market share for each. So we're looking at something that will create some wealth and hopefully also profit for the companies that are involved. And so, so mainly building integration and portable. So, with that, I'm coming to the end. My time is over. I apologize for having rushed through some of the slides, but in the interest of time, okay? And that's some of the organizations that have supported us indirectly or through the awards that have been given to me. And this is our campus here in Lausanne, and we still have snow in Switzerland. Just had our skiing day a couple of weeks ago. So thank you for your attention.
Well, thank you very much for your very inspiring talk, and I think we have plenty time of questions from the audience. So the discussion is open. Maybe I start with a question for you. So what do you tell people who are concerned about the perovskites containing water-soluble lead compounds?
Yeah, well, I was greatly concerned myself, to be honest. So, and in the review in 2014, I made a statement that one has to get rid of the lead and replace it by other metals. But I have actually changed my opinion on this because, after all, we have catalyte, which uses even more dangerous elements than the perovskites. And it sells a gigawatt, it's safe, it's being recycled, but it's mainly used for solar farming. So we made this point this morning. So as long as you contain the system and suppose you have a fence around the installation, you have a 100 megawatt installation, you put a fence around it, put some concrete base, then I see no real problem with that. Okay. So we see a problem if you want to use it for flexible cells. So there are some restrictions that will be hard to sell to the environmental organization, a flexible cell based on lead perovskites. But I should also mention to you that the research on lead-free materials is advancing. And for a while it looked like we won't find anything, but it's always dangerous to make dogmatic statements. And so, recently with the 2D perovskite, two-dimensional tin has come up, and I have been at three perovskite conferences this year, and I can tell you the advances being made on bismuth and tin perovskites. It doesn't have to be a perovskite. We are not married with perovskite. It could be any pigment, okay, that has this reasonably long carrier lifetimes. We can collect with the mesoscopic scaffold. So there are many, many options. And it's just that, what is amazing with the lead compounds is that they have in no time beaten the market leader silicon, which is around for 70 years. So that's really amazing. And using a film thickness that is 1,000 times thinner, okay? So you lose about 1,000 times less material than silicon. And don't tell me silicon is cheap. It cannot be cheap because there's a huge energy investment to make those. And if you look into the carbon footprint of silicon solar cells, it's 24 grams per CO2 per kilowatt hour. That's not small. Okay? That's not small. I guess with the perovskites we can come down to 5. Mm-hmm. So there are many issues still there, And the lead issue, what I would say is, especially if you work with a cell, have to be careful. Don't spin coat these solutions in open air. So we have very strict rules. We have 3 labs dedicated to PSCs, and we keep all the precautions.
Okay, thank you. Are there any other questions?
I think you touched already a little bit on that, but for that Kindle device or the e-reader, there was something said like eternal lifetime. And I assume
eternal battery life, yeah.
Yeah, right. That was the question that I was about to ask. I mean, in terms of battery life, but of course, maybe not in terms of the solar cell itself. So what are the lifetimes of these cells compared to silicon? I mean, if you put something on your roof, you expect to last it for 20 years or so.
Yeah.
Is that realistic, or
for the glass cells? By all means, because these they have passed all the ISC norm tests. And company H-Class, the CTO is somebody from the Swiss who worked before as a manager on our PV test station in the Subsee in the southern part of Switzerland. So the company has engaged the best the technical people, make sure that the norms are fulfilled. So from that point of view, I think the flexible is a different story. But when I said eternal battery life, please it didn't say eternal cell life. I said battery life. What that means is that since you're recharging a battery all the time, okay, you can use it forever. Of course, once the battery falls apart, then that's a limitation. But at least you're not draining out the power out of the battery because it's continuously renewed, and it's enough to have it in ambient light to do this recharging. That's what that statement means.
I would like to see some hands going up from the PhD students in the back. What about you guys?
Don't feel shy, but there is a question here.
Thank you. Maybe I would like to elaborate a little bit on what was just asked. Do you see in your cells kind of a degradation effects? Because in battery we think a little bit that there is a reason why you would see a degradation after a certain lifetime. So in comparison to other cells, is there a reason that you would see in perovskite cells kind of degradation after some years due to the mechanics of the cell?
Are you talking about the dye-sensitized or the perovskite solar cells?
Well, the question is
because the dye-sensitized is now established technology, is being sold, and we have done all these testings. Probably have done with the DSC more stability tests than anybody else, because we had a lot of critics that would say this is not stable, and so you had to time and again show that these cells can be easily stabilized based on electrolyte and dye, or solid-state electrolyte. So today's DSC, they're being sold. So if something goes wrong, the producer has to replace the cells. But now with perovskite, it's a different story. This is still, recently we published a paper in Science on an inorganic whole conductor, copper thiocyanate, where we could get 1,000 hours full light on a cell, okay, full sunlight. And we did it at 65 degrees. So that's a IEC norm. 1,000 hours maximum power point tracking all the time. So how much is it real? At least factor of 11. So 1,000 hours, 11,000 hours. And that's already about, say, 1.5 years, roughly speaking, okay. So these stability tests have been comforting in the sense that we didn't see any degradation. We saw a huge degradation when we had some kind of a problem with the back contact, but not with the photoactive material. So believe me, I was a very critical examiner of the perovskite technology, and we were looking for the weak point. Okay, and so far, people have said yes, there is some ionic conduction. Yes, but I mean, some of these materials, they go through thousands. Like just now in China, I saw an experiment, thousands of hours of laser light on the perovskite, nothing changes. And so the material itself is not photo unstable. And It's the contacts, some issues, so you have to be very careful. The interfaces. We're discussing with our colleagues this morning, the interfaces are critical. What do you use to extract the electrons and the positive carriers? And there we have made huge progress. The latest, I showed you the example of our improvement over the state-of-the-art, 22.7. We were able to improve our state-of-the-art by using modulators that slowed down interfacial recombination of electrons and holes. So these things have to be well controlled. And so the field is still evolving. The jury is not out entirely, okay, on this. But so far so good, okay. We didn't find that that problem that would be the killer. And so
also not the temperature, for example?
Yes, even temperature. I mean, several years ago, we went with the most simple material, perovskite material, methyl ammonium lead iodide. We had done the temperature test. The standard is 85 degrees at 4,000 hours, okay, in the dark. It should also be 85 humidity. Okay, it's called the heat dam test. We did only the heat test because humidity, I mean, that's a ceiling issue. So and we actually did 90 days. It was a mistake. Somebody forgot to check. So the cell was right over 90 days instead of 45 days. Still stable. So I consolidated my view that there's nothing wrong with the perovskites, really, unless you exposed to poor moisture and some issues there, but they're not really, new formulations are not really that moisture sensitive. With the modulators, you can put hydrophobic protection. That's not an issue, really. So there's real hope that you will come up with a device you can sell, and it will be stable and will compete with other technologies.
I have a question, if it's allowed. No PhDs. One thing went a little bit fast for me, but I have seen that you have a nice cooperation with the Lomonosov University in Moscow, and we were working with Alex Tarasov and Eugene Godilin. And Alex Tarasov 10 years ago was here, and we did together.
Yes, I know. He told me.
Okay. We developed together a new route for the synthesis of titanium dioxide. And I just was interested if you developed this further, or even did you use those type of particles from Alex, what he developed?
Yeah, it's a good point. Yes, actually, I met Alex by coincidence. He was driving me from Domodedovo airport to the city. I had to give a lecture at the Nano Congress. There is a Nano kind of, it's called RAS Nano, it's called. So they have a yearly congress for nanotechnology, and they had invited me, and he was supposed to pick me up. And then we started talking, and he mentioned to me that he was, and so I told him, I said, Alex, I want to ask you a question, which will tell me whether you have good chemical intuition. He was the question, I said, how can you infiltrate the mesoporous structure in a non-conformal way? And he came up with the right answer. He said, supercritical CO2. And so, wow, this guy is really sharp. So two of us started to talk, and then we finally launched this joint project. But I know he has been here, and have you used his TI too? Maybe in Russia they do. He has now a group of his own, and he has abandoned his industrial career. He's now a PhD, and he's probably going to be a professor sometime in Lomonosov. He's a vice president of a joint Chinese-Russian university in Shenzhen. So Alex is busy.
The world is very small.
Yes.
So, not exactly a PhD student, but we're coming close.
Not really. To beat the silicon technology, you have to be cheaper than silicon, which not only includes the material price, but also the system price and all that stuff. So you showed some numbers about development of the market shares of these different materials. So where can the perovskites be cheaper than silicon? What kind of areas you think it will beat the silicon technology?
Well, already the energy payback time is much lower. Efficiency is now higher than at least the polycrystalline. We have, I mentioned to you, the carbon footprint is lower. The production cost, well, materials cost is certainly lower. I mean, you can't tell me that polycrystalline is, silicon is negligibly cheap. It cannot be because it has an energy cost. So it has to have six nines to be. I agree, it's made at large scale and the cost has come down, all of this. But there's a technology you can paint. It's a kind of the dream of a PV. You can paint it on a support room temperature solution and no energy input required. You can use off-the-shelf chemicals. Contact materials can be cheap. We have shown that with copper thiocyanate recently. 1 gram costs $0.5. So it's a threat to silicon. I'm not saying it's for sure to beat silicon, but it's a threat.
So I see no further hands. That means we are almost at the end of this symposium. So first of all, please join me in cordially thanking Professor Graetzel to come here to KIT and give his very nice presentation. Then we should also thank the team from the Global Energy Prize who made all this possible. Thank you very much. And last but not least, we also had something which we can consider a local organizing team. This was Heike Kull and Mrs. Legand. Thank you very much for organizing everything so that we had such a nice event here. So the last thing that remains to be done is to invite you all on behalf of KIT and its Energy Center to a reception. We have some drinks and some food outside, so when you get out, take the opportunity, grab some food. Do not just escape through the elevator, but use the opportunity and discuss a little bit about science, about solar. Take the opportunity to talk to Professor Graetzel. That's an opportunity you will probably not have so often. So he is here today. And yeah, thank you very much for coming.